Sciences, ISR Kolkata. So he is working with Professor Saurin Das. His areas of research are condensed matter physics, non-Hermitian physics, and quantum entanglement. So, Anant, you can start.
Yeah, sure. Yeah, so hello everyone. My name is Anant, and first of all, I would like to thank the organizers for this opportunity, especially Panigrahi sir for consecutively giving me this chance. And so what I'm going to talk about today is the temporal correlations in different non-unitary quantum dynamics and their realizations. So here's the outline. First, I'm going to introduce some dynamical maps, which would comprise of different dynamics, non-unitary dynamics. I'm going to define what, in particular, what non-Hermitian dynamics is, and then I'll move ahead and define another idea, which is the Leggett's inequality, and which is used to probe the nature of the dynamics from classical and quantum, to differentiate the dynamics between quantum and classical regime. And then I'm going to show some results and related to the non-Hermitian dynamics, and then I'll show how to realize these non-Hermitian dynamics and how they are different really than the other open quantum system dynamics that we see around. And for the completeness and to contrast with the another set of non-unitary dynamics, I'm going to talk about the quantum nature of Markovian dynamics. And so with that, I'll conclude. Fine. Yeah, so let's have a look. Let's first have a look at the different set of dynamics that are available there. And I'd like to draw your attention to this portion here, this green colored set here. So obviously the well-known unitary set of dynamics is here. But then there is another class of dynamics, which is known as unital in literature. And the key property of such dynamical maps is that the purity of the quantum state as time progresses during the dynamics is strictly a non-increasing function. So which means that either the probability will, either the purity of the state will stay the same or it will decrease. Of course, the well-known example that we are aware of, which is a subset of this class of dynamics, is Markovian dynamics, where we know that the purity or the coherence of the state really decreases in time. But then there is yet another set of dynamical maps, which is known as non-unital maps. And now the key feature of this is that here the purity of the state can be increased as the dynamics progress. And a well-known example, of course, is what is non-Markovian dynamics that we are aware of. That there, of course, quote unquote, we say that the information can flow back from the environment to the system. So that's it. With these three different classes of dynamics, what they define together is a full set of all possible quantum mechanical dynamics that are considered physical in quantum mechanics. Now I need to define what do I mean by physical. So if you pick any operator or any dynamical map from here, and if you apply over a state, then the resulting state should follow the following should have the following properties, that the resulting state, the trace of the resulting state of the corresponding density matrix should be preserved, which means the total probability of any quantum state should be preserved. And then, of course, the positivity of the state should also be preserved, which positivity of the probability should also be preserved, because, and that corresponds to the eigenvalues of the density matrix. The eigenvalues of the density matrix should be positive. And so with these two properties, what we can call a quantum state as a valid state. But this state has this third property, which we usually kind of ignore or do not pay much attention to, is that all these maps are completely positive in nature, which means that if we use any of these operators and use them as a local operation, then the resulting total state should also be a valid quantum state. What do I mean by that? So suppose that we have a bipartite state rho AB, and if I choose an operator which is a local operator, which is acting on only part A, so it's a local operation, and so this resulting state, even this resulting state should also be positive. So that's what I do mean by when I say this map, these maps form the what is known as completely positive maps. But then outside this set of maps, you will see that there is another class of dynamical maps which follow these two properties, that when the trace of the density matrix as well as the positivity of the eigenvalues are preserved. And these dynamical maps, which you can see here, this one outside this region, are known as strictly positive maps, if you like. So suppose if you have a state rho A, and if you choose an operator from this class of operators, and so you will see that the resulting state is a valid quantum state, meaning the trace is preserved as well as the positivity is also preserved. However, what is the difference here is that if you take a bipartite state, so for example rho AB, and if you use these maps as a local operation here, then this resulting state may or may not be positive. So which means the eigenvalues can go negative, or in other words, the probabilities would turn out to be negative. To give an example of this, a well-known example in quantum computation and information is the example of transposition. So suppose if you have a qubit state over which you apply this operation of transposition, you know that this resulting state would still be a valid quantum state. However, if we start with the Bell state and then only apply this transposition operator only on one of the qubits, then this resulting states would not give you a positive density matrix, meaning the eigenvalues are negative, or the probabilities would become negative. So, so with that, what I'm going to talk about is especially this set of dynamics, which comprise of this PTB is the PT broken dynamics, and PTS is PT symmetric dynamics, and then rest of this part comprise of all possible non-Hermitian dynamics that are there. And the point is that, or in the rest of the talk, what I'm going to do is going to tell you in more detail that what are the differences between the dynamical maps which are here, than the ones which are here. So difference between a positive trace preserving maps or between the completely positive maps. So that's all I'm going to do. So even if you miss out a little bit of information there, that's more or less the message is that how so I'll tell you in more detail that how these maps are different than these. That's all I'm going to do. So now consider one of the corresponding operators from this outside set that we saw just now, a non-Hermitian operator for a two-dimensional system. And of course, for a two-dimensional system, if we have to write a non-Hermitian operator, what we can do is that we can write down a Hermitian part, which is defined by this A dot sigma, and then we can write down the anti-Hermitian part, which is defined by this IB dot sigma. And if we have such a non-Hermitian Hamiltonian with the eigenvalues, with the eigenvectors phi plus and phi minus, so and if we calculate these expectation values, we'll see that the real part of the course would correspond to this operator A dot sigma, while as the imaginary part of the eigenvalues would correspond to the expectation value of this another operator B dot sigma here. And what I'm going to talk about, particularly in this talk, is when this number is 0. So only the non-Hermitian Hamiltonians which have real eigenvalues. And so given this non-Hermitian Hamiltonian, what we ask is, what is the corresponding dynamical equation which governs the evolution of a state? So if we take this non-Hermitian Hamiltonian on board and write down the dynamical equation for it, this is the dynamical equation that you get. And important thing to notice here is this, in particular, is this third term, where you will see this term is non-linear in rho. So because there are two of them. And so essentially, in this context, non-Hermitian dynamics essentially is a non-linear dynamics. However, unlike many other non-linear dynamics, what we can do here, we can exactly write down the solution of this equation in this form, which looks quite familiar, because we know that in case of Hermitian quantum mechanics, the solution to the dynamical equation would be this, and it has just another normalization factor, which is nothing but the trace of this resulting density matrix here. Now, like any other Hermitian dynamics, this also has two fixed points, which are the two right eigenstates of the non-Hermitian Hamiltonian. And so you can check that with these phi plus and phi minus which we initially defined, are the two fixed points of the dynamics, meaning the rho t is equals to rho 0. If these are the initial states that we start with. Right. So now if we want to stick to the non-Hermitian Hamiltonians, which only have real eigenspectrum. By the way, this can happen. So what is the condition for that? This is something now we need to look at. And this was found by this was written long ago by Jordan. The necessary and sufficient condition for any non-Hermitian operator to have real eigenspectrum is the following condition, where if this equation follows, where this operator eta is a positive definite operator, if you can find such operator for a given non-Hermitian Hamiltonian, then this non-Hermitian Hamiltonian is guaranteed to have real eigenspectrum. Of course, of course you can see immediately that if this Hamiltonian has a real eigenspectrum, what you can do this kind of similarity transformation where this small matrix H is some diagonal matrix which has real entries in it. And this similarity transformation S here is some general linear operator, which you can further decompose as a product of two operators. One is a positive operator, another is a unitary operator. And from this straightforwardly, you can check that the eta matrix that you will get is a positive definite operator. And in particular for a two-level system, you can always write down any positive definite operator in this exponential form. We'll see later on what is the importance of this eta when we'll try to realize this non-Hermitian dynamics using quantum mechanics, of course. So now I'm going to introduce another idea, which is this non-negative inequality, which is used to classify the dynamics from quantum to classical or otherwise, or the other way. So the basic idea here is that if we want to claim something is quantum mechanical in our system, what we do, we make certain observations. And if these observations cannot be explained by using classical postulates or classical rules, but can only be explained by quantum mechanical postulates, then we claim that whatever the assumption, whatever the observation or the phenomena that is there is a quantum mechanical phenomena. So in a similar spirit, this inequality is also defined. And what we do here is that we calculate some ensemble averages or the expectation values of observables in quantum mechanical language, if you like. So these are the expectation values of some observables that we calculate. And then what we do, we take a special linear combination like this, and then we ask this question that if we would have followed the postulates of classical mechanics, which are these two, and I'm going to define them in a minute. But if you follow the classical rules, then what are the bounds on these special linear combinations? So this is the usual way to what do I mean by when I said that I'm going to tell you about the temporal correlation. This is what do I mean by that. That if you take this special linear combination and if you ask what is the bound on this correlation, if you would have followed a classical rules, and if you would have followed quantum mechanical rules, of course you could violate a certain number which is available there. By the way, this kind of combinations are not unique. So you can, of course, if you want to ask in your particular setup that whether this is a quantum mechanical, whether there is a quantum mechanical nature existing in your system or not, you can also define your own observables, of course, and take any other combination of your choice. But of course, then this would be bounded by a different number that you need to work out. But the more important point is that these are nothing but some expectation value of or the ensemble averages of some observables. Was linear combination we are asking question about what is the bound on that linear combination. Okay, so here is a typical Legge-Decker experiment is done. So what you do is that you start with a state psi independent of where it has come from. And then what you do, you measure the state at time t1, and you measure the state again at time t2, and then you do the same thing by creating an identical copies of your experiment, and you repeat the same measurements at time t1 and t2, And that's how you create a single ensemble. And with using the data that you get in this ensemble, what you calculate is you calculate this ensemble average, which is QT1 and QT2. And of course, this in this case, what these QT1 and QT2 are nothing but two dichotomic observables. What do I mean by a dichotomic observable? That their eigenvalues can only be plus or minus 1. And that is why you see the number, this number, why there is a number which is 1 here. And the reason that is bounded by 1 only, because these observables are dichotomic numbers only. Their eigenvalues are just plus 1 and minus 1. So we create one ensemble and calculate the average value, just like we do in any experiment. We tabulate all the outcomes and calculate the average value. Similarly, we create another ensemble, and of course, with a similar initial condition, the state psi is also again the state psi here. But instead of measuring at time t1, what we do, we measure at time t2 and t3. And similarly, we create another ensemble where we measure the state at time t1, but not at t2, and directly at t3. So that's how we create 3 different ensemble averages, and which are given by these C12, C23, and C13. And now the question is that if we would have followed the rules of, if the system, the dynamics of the system is classical, or follow the classical rules, which were these 2 assumptions that I showed you in the last slide, which are the macroscopic realism, which states that a system can be in only one of its many macroscopically distinct eigenstates for all times, whether it is measured or not. So that's the first rule. And if we take this assumption on board, and if we assume these, which essentially implies that these numbers, this Q1, Q2, Q3, can be treated as numbers. And what you can then immediately check that if these 3 are simply numbers which can either take values of plus 1 or minus 1, this suitable linear combination would never go above 1. And if that's the case, if you would have created any ensemble out of it, and if you again ask this question whether this ensemble is bounded by 1 or not, so since the number themselves are bounded by 1, the ensemble, any ensemble that we'll create will also be bounded by 1. Now comes the next assumption, the second assumption, which will define the classicality for us, and which is the non-invasive measurability. And what does it say? That any measurement that you do on your state is not going to perturb the dynamics or going to collapse the state to anything else. And so if we take that also on board, then what we can see that this ensemble average, which is just a mathematical exercise, is going to be equivalent to what we calculated using what we use to get our ensemble averages in the experiment. Because essentially what you're doing, you have 3 ensembles which you are going to compare with a single ensemble, and so unless these measurements do not affect the dynamics of the state, we are good to compare these 2 ensemble averages with each other. So that implies that any violation of this inequality is not necessarily implies that it's a violation of classical mechanics. It could so also happen that the measurements that you're doing in your experiment are invasive in nature some way. So that's one loophole of this inequality, if you like. And so in quantum mechanics, of course, one need to show that this inequality gets violated. So the quantum mechanical version of these correlations, these numbers that we define, is nothing but an anti-commutation expectation value of the anti-commutation of the observables, which can be written down in this form, because as I said, these Q's are nothing but dichotomic observable, and any dichotomic observable for the 2-level system you can always write down as some unit vector n dot sigma. And if you do that, the resulting answer to each correlation would boils down to asking this question, that what is the angle between the 2 unit vectors. And of course, then the angle between the dot product can be written as cosine of the angle between the 2 vectors. And if you do that, then we can easily see that once this value is, let's say, pi by 3, each of these angles, the number that we get for K3, or this linear combination that we had written now, is going to be 3 by 2, because each of these correlations are going to be half, half, and minus half. And so in quantum mechanics, this violation can be maximum up to this number only, which is bounded by 3 by 2. And so the point is that now one has to also make sure that the measurements that you did were non-invasive in nature. And so in order to ensure that, if we can make sure somehow that the probability of measuring any state at time t2 is some way is independent of whether we measure something at time t1 or not, we then of course can claim that whatever the violation that we are showing is because of quantum mechanics and not because of the invasive nature of the measurements. So in order to make sure that these probabilities stay independent, later on we'll use another condition which is known as no signaling in time. And yeah, so here is another case which you can see. So this is a Mach-Zehnder interferometer setup where you can see that you can even violate this inequality. And so even if you would have done this experiment Mach-Zehnder interferometer with a classical light, even you will still be able to violate this inequality. So the point that I'm trying to make, that this violation essentially need not to imply that you have something quantum mechanical in nature. You have to be careful. It could be because of, see, as this because of the similarity between this wave mechanics and quantum mechanics in optics. You can see that even with the classical light, we can do is that we can violate this this inequality, which has nothing to do with the quantum mechanics. Yeah, anyway, so now let's come back to the dynamics that we had in hand, that this non-linear dynamics, non-Hermitian dynamics. So if we stick to the regime where the eigenvalues of the non-Hermitian Hamiltonian are real, and ask this question, how the trajectories on the Bloch sphere, since it's a two-level system, we can always ask this question of the state evolution on the Bloch sphere. If we ask this question, what are the trajectories on the Bloch sphere looks like? And it turns out that in this case, when the eigenvalues are real, all the trajectories on the Bloch sphere are going to be periodic orbits. So just like, you know, Hermitian quantum mechanics. And what essentially another feature that one finds out, that all the geodesic paths are also allowed. So geodesic meaning this big circle that we have, you know, like equator and so on. So these are also the solution of this dynamical equation. And so that naturally allows us to compare any Hermitian dynamics with this kind of dynamics. So that is something that we do next. We ask this question that, let's say if we stick to the geodesic path and we use this non-Hermitian Hamiltonian, and of course we know for sure that we can always define a Hermitian Hamiltonian, which is pointing along x direction. So let's say if I have a Hermitian Hamiltonian sigma x, then and if I choose an initial state on this geodesic, I would always keep on processing on this geodesic, right? With a specific frequency, which is known as Rabi oscillation, if you like. And so, but even if your Hamiltonian is non-Hermitian like this, even then your trajectory is a geodesic. The only difference that now has come is that now even though the Hamiltonian was static Hamiltonian, the state that is going to evolve on this geodesic is going to be accelerating. So, you know, with only a static Hermitian Hamiltonian, when a state is evolved in a perpendicular plane, it has a constant frequency which you could call is Rabi oscillation or whatever, with a fixed frequency or the fixed velocity. But now here you can see that on the same trajectory, if you use a non-Hermitian Hamiltonian to evolve a state, it is going to be accelerating. And so now, if once we see that there is an acceleration, we need to define a notion of what is known as speed of evolution. So how that is done? We take the state at time t and time t plus delta t, and then we expand it in terms of delta t up to first order, second order. And then what we do is we look at these coefficients, which are nothing but the variance of the energy expectation, if you like. So, and these are the energy fluctuation, which we can regard it as a speed of evolution of the quantum state on this Bloch sphere. And it turns out that in this case, if you use this non-Hermitian Hamiltonian h of theta, the speed of evolution is going to turn out to be a time dependent. So, okay, one more thing, mind you, this whenever I write this t, this is going to be time interval and not just time, because, you know, it's just I'm really sorry for that, but this t, whenever you see, it's just a time interval, unless I'll tell you otherwise if it is not. So it is a function of time interval. And if you can imagine that in case of Hermitian Hamiltonians, it is never possible to have an acceleration. Of course, you can have an acceleration by defining a time-dependent Hermitian Hamiltonian, which would accelerate your state because you can vary your Hamiltonian. But what you cannot do, you cannot get a speed of evolution which is time interval dependent rather than explicit time dependent. So this is the reason why we are going to see that certain correlation, temporal correlation, would go absolutely beyond what you would expect in a quantum mechanics.
Anand, sorry to interrupt you. You have 5 more minutes. Okay.
Yeah, sure. Okay. Yeah, fine. So yeah, so here you can see that this is the block oscillation. As you can see, it's periodically changing after equal time interval. It's traveling equal distance on the block sphere, because this theta is 0. Theta you can consider as some non-Hermitian parameter, and if you increase this non-Hermitian parameter, you can see. Okay, so for when the theta was 0, you can see this here. The speed of evolution is a constant. When you increase this this non-Hermitian parameter theta, which would make your Hamiltonian non-Hermitian, of course, when it is non-zero, you would see that the speed of evolution have some acceleration in it. And so if you go ahead and calculate this LGI for what, like we discussed, that calculate some ensemble averages and so on, for this kind of dynamics, what you find is something rather unexpected. So what we already said, that in quantum mechanics, this bound is going to be 3/2, which is this dashed line here. But what we found, if we choose any value of theta, non-zero theta, which means the Hamiltonian is non-Hermitian, we find that this bound is always violated. So even the quantum mechanical bound is getting violated. So now we have to be very careful with the interpretation of this, whether this is a violation of quantum mechanics or it is somehow we are making non-invasive measurements and so on. So and so in order to do that, what we first ask is that so first we got this violation here. So the natural question to ask is whether even this dynamics is possible to realize in some physical systems or not, or it is just a mathematical exercise. Because since you see that this bound is going above quantum mechanical bound, so it probably is just some mathematical exercise that we are doing. But it turns out we found this experiment in this paper, where what was shown is that using some optical setup, what we can do is we can create the dynamics that I just mentioned you, that the dynamical equation that we wrote down. What you can do, you can use an optical setup with all these details in it. I'm not going to into, but what we did, we compare our data of dynamics with their experimental data, and we were kind of relieved that at least there is an experiment which can simulate this dynamics for us. And so from there, of course, we get on to move ahead to asking this question, that how to realize this dynamics within the framework of quantum mechanics. And so now the question again boils down to that if you have a state psi, and if you want to evolve this state psi using a non-Hermitian Hamiltonian, then what you'll need another spin, let's say example. So if this psi is the state of a qubit, then you're going to need another qubit such that, and you will allow them to interact such that the total Hamiltonian that you will write is going to be a Hermitian Hamiltonian. So now, of course, this is something we know, that the Hamiltonian is Hermitian. You have 2 spins or 2 qubits, whatever you want to call them. So now we have a Hermitian Hamiltonian, which we are aware of. We can manufacture it. We can set up in an experiment. Then all we need to do, we need to custom design this initial state, which have this particular form. And of course, you can see that this eta that we were talking about earlier has importance of when you design these kind of initial states. And if you evolve this state using this Hermitian total Hamiltonian, what you will see that the state psi, which you wanted to evolve by a non-Hermitian Hamiltonian, is sitting here, right? So this e to the power is theta, this h of theta is a non-Hermitian Hamiltonian. Although you will get to see this state only if you will measure on this this extra qubit that you had introduced, if it only measured in the up ideal state. So all I'm trying to say that the realization itself of this non-Hermitian dynamics is rather different than rest of the open dynamics that we see, because in rest of the open dynamics, open quantum dynamics, what we do usually is we trace out the rest of the degrees of freedom of the environment. But what we are doing here is that instead of tracing out the degrees of environment, which in case is this for this qubit, is instead of tracing out the degrees of freedom, what we are doing, we are projecting this environment degree of freedom to a particular state, which is up of Z in this case. And this is what leads to some loss of data. Of course, if you recall, we had some ensemble averages earlier to write down this LGI. And if you only project it, then you're just throwing away this data. And if you throw away some data in a given ensemble, then of course you can approach any algebraic value of that ensemble that is there. So that's more or less the so that's the difference that I want to point out. That this is how this non-Hermitian dynamics is rather completely different than all the different open quantum system dynamics like Markovian dynamics and so on that we are aware of. Okay, anyway, this is probably, I do not have time for it. Yeah, so this is another study that we did with to contrast the results with the rest of the CPTP dynamics. So now we are asking question about what are the possible bounds within this subset for LGI. And what we found that in this set, you can never go beyond quantum bound, which was this 3/2 that we saw earlier. And so in this sense, what you can think of is that LGI violation above quantum bound, you can think of as a signature of the dynamics which is available here. So that's the message. Yeah, thank you.
Yeah. Okay, so thanks, Anant, for this beautiful talk. So the talk is open for the question. Please feel free to unmute yourself and ask the question. So maybe there is a question in chat box by Devdutt Sharma. He is asking how unital is different from unitary.
Yeah, so in case of unital, in unitary, of course, the purity of the state, if you start with a pure state and if you do the unitary evolution, the pure state is going to stay pure. Or if you start with a mixed state, the purity is not going to change if it's a unitary evolution, because it's just a rotation on the Bloch sphere, right? In case of unital, it is more than that. So the radius of the Bloch vector, if you like, can also decrease. So a pure state can become a mixed state, but not the vice versa. A mixed state cannot become a pure state. So that's what the difference between the unitary and unital. Unital, if you start with a pure state and if you wait long enough, you will end up with a mixed state.
Okay, so anyone has any question? Okay, no. So I want to ask you a question. Just go to the, I don't remember the slide. Where you have written this
sorry,
rho is equal to something. Just go to back here, please.
Which slide are the way?
I don't know. I don't remember. Just go back. Just go back. Yeah, please go back. Yeah. Yes, this slide.
Yes.
Yeah. So you have written this rho t is equal to this thing is. So what will happen is when this is when the state is kind of it is for initial state or it is for the final state. This rho t. Which
so rho 0 is your initial state and rho t is your final state. So if this Hamiltonian would have been Hermitian, as you can see, h, then h is h dagger, so it's just e to the power ist times psi.
And why have you taken this trace of this multiplication? It is for the non-Dyson or something else.
Yeah. So this if you see that if you want to write down the solution of this by solving analytically, even then you will get this answer. But this trace is sitting here just to make sure that the trace of the density matrix is preserved, because and that's why this non-linear term has come. Otherwise these two non-linear term would have because this part is nothing but the one Newman equation.
Okay,
Right.
Thanks. Thank you. Okay, so thanks. Yeah, Abhinav has one question.
Yeah, sure.
So Abhinav, please unmute yourself and ask. Abhinav? Abhinav, are you here? I think, okay, I think he's, 1 second.
Yeah, you have to unmute.
Okay, 1 second. Yeah, Abhinav, please.
You can, yeah, can you hear me?
Yeah.
Yeah, sorry, there is a glitch. Okay, so hi Anant.
Yeah, hi.
My question is, can you go to that plot where you showed that your quantum bound was also getting violated?
Yes, sure. Yeah.
Yes, that one. So here, so my question is that for, I guess, okay, it's too small for me. So maybe the black curve, the black one, right? That is for theta is equal to pi by 2.
Yes.
Yeah. So in therein, but I see there are two singularities.
Mm-hmm.
And
Yeah, so these are not singularities. Sorry. So this number is bounded by 3 only, 3 and minus 3.
Okay.
As you can see, this K3 is. So these are not singularities.
Okay. So I was thinking that they represent acceleration. So how do you explain infinite acceleration? So they are bounded.
Yeah, they are bounded because this function has a range of -3 to +3 only.
Yeah, that's okay. But okay. Yeah, now it's clear. Okay, fine. Thanks.
Yeah, sure.
Okay, so let us, thanks, Anant. Thank you, Anant. Okay, please stop sharing your slide. So
Yeah,
that we
thank
can go
you.
to the
Thank you
next.
so much. Yeah, sure.
So the next talk will be given by Subhashish Barik. He is a PhD student at University of New South Wales. He works in the area of quantum computation and quantum optics. So Subhashish, please share your slide.
Thank you, Dr. Aradhya. I hope I am audible now.
Yeah, you are audible.
Yeah, I'll just share my screen. All right. Is it shared now?
Yes.
Perfect. Firstly, I would like to thank the organizers and especially Professor Panigrai sir for giving me an opportunity to be here. I started my research career around 1.5 years back, around 2.5 years back at ISA Kolkata. And it's a great pleasure to be here today, although virtually. All right. So looking at my slide, seeing the animation, you can get an idea of what I'm going to speak about. It's going to be about photonic quantum computing, particularly about the continuous variable architecture. I have around 20 to 25 minutes, I believe. So I'll try to touch upon different aspects, leaving the details, leaving references as the details to them. All right. So quantum optics has two regimes. One is discrete variables, where you talk about single photons, and the other is continuous variables. So we'll start with continuous variables. Then we'll go and see how continuous variables can be further extended to make very large entangled states. And then finally, we'll see how those entangled states can be used to do the fun part, the quantum computation. All right, so let's dive deeper directly into continuous variables quantum optics. I'll just touch upon the fundamental aspects of it. I'm pretty sure you all know this quantum harmonic oscillator and this bosonic field operator, and then the position and momentum operators. They are like this. I believe my pointer is also visible. So the Q and P here are nothing but the position and momentum operators, and K denotes the particular mode we're talking about. Yeah, so this was there right from the beginning of quantum optics, but things became interesting when these two gentlemen, S.L. Bronstein and Seth Lloyd, for the first time used the continuous variables, which are the eigenstates of position operator, as a computational basis to do quantum states. We know about qubit, the so-called 0 and 1, but then it can be also shown that it was shown by these two gentlemen that we can use the position eigenstates and the momentum eigenstate as the computational and the Hadamard basis for doing quantum computation. And it was around in 1999. Also, something intrinsic to continuous variable is this phase space representation, where we measure the probability distributions of the position and momentum. And in order to measure the probability distribution, we take the help of two statistical moments, which are nothing but mean, the x, and the variances. So the variances are expressed in terms of these covariance matrices, whose elements are given by this. And since most of the quantum states take of Gaussian statistics, we nicely describe them using this so-called Wigner function, and you can look that they already take Gaussian function, structure here. And this led to the idea of Gaussian quantum information. There's a nice review by Wiedbroek on it as well. Next, something that is at the core of quantum optics, core of continuous variable quantum optics. In fact, it's the heart of continuous variable quantum optics is squeezed light. And it is literally heart because we can do wonders using this squeezed light. And we can mathematically describe the squeezed light using its operator, which is like this exponential raised to a and a daggers, the second power of it. And we can also write it in a nice matrix form using this. And producing the states is not enough. You need to detect them as well. So something that we widely use in continuous variable is called homorine detection. And the way we detect a quantum state is by interfering the signal that we want to detect with a very strong signal called local oscillator on a beam splitter, and then take those two output modes and then subtract and get something like this subtracted current. And from that subtracted current, we can easily find the quadrature variables. So we can measure the Q and P and look at the statistics. And this theta here gives you the freedom to choose whatever quadrature you want to look at. So you can basically look at any direction of the phase space depending upon the phase difference, the theta that you set between these two modes. All right, so we went through the fundamental aspects of continuous variables. Now let's go to continuous variable cluster states, how we make cluster states and do measurement-based quantum computation. So a quick overview of measurement-based quantum computation here. Okay, this is a bit problematic. All right. So the idea dates back to around 2001 when Robert Russendorf came with this alternative idea to do what we call as the gate-based quantum computation. So in his claim, all we need to do quantum computation is a very large entangled state and a set of projective measurements. Now, projective measurements are not difficult because you anyway do it in gate-based model, often during the end of the quantum computing process. But for cluster state-based quantum computation, the measurement-based quantum computation, what we do is we take an entangled state, a large entangled state, a 2D cluster state, and keep measuring. And as we keep measuring, the information keeps flowing. For the details, you can check this paper. But something phenomenal happened when it was realized for the first time, this measurement-based quantum computation, when it was realized for the first time at Technical University of Denmark, of which I was a part of, although not as an author, in last year. And it was a completely programmable demonstration of measurement-based quantum computation on a large cluster state. And I'll strongly encourage you to look at this YouTube talk by Ulrich Anderson, who was my supervisor and the leader behind this work. All right, now the interesting part, how do we generate the cluster state? Because the essence of doing measurement-based quantum computation is to generate a large cluster state. And it seems that in continuous variable regime, where you do not need single photons and you need squeeze lights, it's rather easier to generate a cluster state, a big one. So I'll divide it into three parts. We'll look at the idea, the principle behind it, then we'll look at the setup, and then we'll look how actually things look in the lab. So the idea is very simple. We start with, okay, maybe this will help. So we start with two squeezing sources. We call them optical parametric oscillators. So they continuously emit squeezed pulses of light. And then what we do, we interfere those two squeezed light here on the first beam splitter. And then what we do, we delay one of those squeezed pulses here by one temporal length. By temporal length, what I mean is if two squeeze photons are coming, then two squeeze pulses are coming, then the time difference between these two. So we delay one of them by one temporal length, and then we again put them on beam splitter, and then we again delay one of the squeeze pulse by multiple temporal modes. And then at the end here, we get a 3D cluster state. This visualization would become a bit better if I think I show this video. Just a second. I hope you can see the video now. Yeah. So the two modes start here, and then they interfere on a beam splitter. And then you can see you generate two more entangles here in an EPR state here, and then you delay one of those. And then you further put them on a beam splitter, the second beam splitter. And what you get here is a 1D cluster state. And then you measure them using these two Homoran detectors. So this video shows how, just a second. Yeah, that video shows how you generate a single cluster, 1D cluster state. But to go to a 2D cluster state, you have to further use another beam splitter, and you get a 3D cluster state here. A graphical representation is like the following. So we start with a bunch of uncoupled or separable squeezed modes, and then you interfere them on the first beam splitter. Where is my, yeah, interfere them on the first beam splitter, then you generate EPR states, then we further interfere them on the second beam splitter, and then we generate a 1D cluster state, and finally we get a 2D cluster state after the third beam splitter. But this is just for the representation's sake, this circular nature. In general, in reality, it's a planar cluster state. It's a two-dimensional cluster state. Well, the principle is quite simple, but if you look at the setup, the experimental setup, it is not quite so. This slide looks pretty overwhelming, I know, but the message that I want you to leave with is that there is a lot of electronics that go behind an optical circuit. Particularly, like you can see, after every interference, after every beam splitter, we have this arrow, this triangular thing. So it is here, it is also after the second beam splitter here, also after the third beam splitter here, and also after this homodyne detector beam splitters here. So they basically control the interference, because you need to have very nice interferences of the two modes. And the way you control them is you first look at the result of that interference and see how bad they are, and then you compensate for that bad phase difference by feeding it back to the previous step. So yeah, but all those things are still on paper. In lab, it looks something like this. So you have a hell lot of optics, but the most interesting things are the two squeezers, these two boxes covered by these glass lids, and they generate squeeze light by being pumped from this second harmonic generator. So you start with the 775 nanometer light from here, and then use those two lights to pump these two squeezers, and then they produce squeeze light. And then you take those squeeze lights and use through these fibers here to make a cluster state. And notably, you can see the two delay lines here, one this white box, which is like the long delay line to generate the 2D cluster state, and the short delay line, the smaller one here, to generate a 1D cluster state. And here are the two Homodyne detectors. All right, so we looked at the cluster states now. Now let's see, the next thing is how do we use these cluster states to do quantum computation? So I'll briefly touch upon how to make a quantum computer. What are the necessary ingredients to make a quantum computer? So three necessary ingredients to make a quantum computer are universality, scalability, and fault tolerance. So we'll look at each of them one by one. Talking about the universality, universality, we say a quantum computer is universal when it is able to implement all kind of quantum gates, all. And the requirement in general to make a universal quantum computer is to have both Gaussian gate and non-Gaussian gate. They translate to discrete variable quantum computation like Clifford gate set and non-Clifford gate set. If you just have Gaussian gate set, then it is not enough to do quantum computation. I mean, true quantum computation, something that a classical computer cannot do. So in continuous variable optics regime, you need these three gates. First one is the displacement, second one is the squeezing gate, and third one is the Fourier transforms that take from you to the Q space to the P space. For using this, you can have single mode Gaussian universality. If you include a 2-mode gate, the simplest being the beam splitter, then you can make a multi-mode universal Gaussian set. And then you need a non-Gaussian operation like this cubic power. So everything that stays up to the second order in Q and P in your quantum gate operation structure, it's Gaussian operations. Something that goes beyond this two. So if you have cubic or fourth order or fifth order in this, then you have a non-Gaussian operation. So far, we have already demonstrated this two, the first two, this Gaussian set. It was demonstrated in the Nature Physics paper that I showed you a couple of slides back. And this part, this non-Gaussian part is still a challenge. It's quite hard actually, and it's still not been generated. But then there is something interesting that came up from the group of Nicholas Menikuchi in Australia, which said that you can do universal quantum computation without having a non-Gaussian resource, but then you need to have something called a GKP state. They're very famous in optical quantum computing, and they are used particularly for error correction. I'll not go into very detail about them, but I'll mention them in the fault tolerant thing. But for that, you need to have a GKP state. If you just want to do universal quantum computation using a Gaussian states, then using Gaussian gates, then you need to have this GKP state. But if you do not have a GKP state, then you better come up with something non-Gaussian. Where's my question? Yeah. So this gave us an idea to go for, just a second. Yeah. Where's my cursor? Yeah. So this gave us an idea to go towards the non-Gaussian cluster state. Now, why do we need a non-Gaussian cluster state? Of course, we need it because we need to do something truly quantum, which a classical computer cannot do. And these papers, they actually showed it very rigorously that as long as you have a Gaussian cluster state or all Gaussian operations, you cannot have something that cannot be done by a classical computer. So you need to have a non-Gaussian. You need to have non-Gaussian elements. Now the question comes to how you bring non-Gaussianity, and some standard methods are to go after this photon number resolving detectors or by photon subtraction. If you use the photon number resolving detectors, you make your detector non-Gaussian. And if you use the photon subtraction, then you make your state Gaussian. But then the first approach is quite difficult because photon number resolving detectors are still to work very efficiently, and they're also very expensive. So many groups, they go after photon subtraction. So in photon subtraction, what you do is you take your Gaussian state and you try to take some photons out from those Gaussian state, and whatever left is a non-Gaussian state. So we try to implement that thing to our cluster state. And the idea was to subtract photons at different points in the cluster. So like I mentioned, you start with the EPR state, and then you make a 1D cluster state, and then you make a 2D cluster state. So the idea was to try to look how things become when you subtract a different location. And we drew the motivation from this paper, where they implemented photon subtraction on their cluster state, but then they had a very small cluster state, like 4 modes. And we had a large cluster state, like some 30,000 electromagnetic modes of Swiss light. Yeah, so the idea was to, try subtracting at different locations of the cluster and see how the non-Gaussian behavior comes up. And in order to pursue that, I started with some simulation work. And in the simulation, I got some results which hinted towards some non-Gaussian peaks. So here you have 3 graphs for subtraction at different locations in the cluster. And you can see that I'm subtracting here at this point, okay? And this peak is a signature of non-Gaussianity. It shows a higher quadrature variance. If you just have a cluster state, a Gaussian cluster state, you have your squeezing, like you have your quadrature variance like this 1.6. But if you have some subtraction and some non-Gaussianity, then these peaks indicate. And you can see that if I'm subtracting a photon from here, something I forgot to mention, at all these 3 types, I have subtracted only at one location and saw how the non-Gaussianity has affected to different neighboring modes. So for EPR state subtraction at EPR location, I got 2 peaks here. For 1D cluster state, I have more picks because now in a 1D cluster state, you have more links to different modes. So if you are subtracting at one location, then the non-Gaussian spreads. And the subtraction at a 2D cluster state, you have further picks. They show that you have the non-Gaussian spreaded across even more modes. And in order to quantify this non-Gaussianity, we have to come up with a measure, and we use the same measure that the people in Treff's group used, the nature physics paper that I showed in previous slide. And we tried to see how the excess kurtosis behaves. So excess kurtosis is nothing but the fourth order statistical moment. And this is actually a measure of classical non-Gaussianity, but it was easy to implement this experimentally, and we just stick to this measure. And then we saw that we simulated that we need to have around minus 0.25 excess kurtosis, and here minus 0.08 and minus 0.25 here for showing some non-Gaussianity in a cluster state. But then simulations and experimental results are quite different, and what I'm going to show you might shock you a bit. So I went to the lab and then I experimented, and I saw some peaks when I subtracted from the EPR state, like these 2 peaks here. When I subtracted from 1D cluster state, we were expecting more peaks in the neighbor because now your cluster state has linked more modes, but that did not happen. And similarly, it did not happen at the 2D cluster state level as well. And the reasons are pretty obvious. A lot of experimental imperfection. There are experimental imperfections in photon subtraction and also at the phase stability of the detectors, so on and so forth. So this thing is still going on in the lab. People are improvising it, and when we get some good results, it will be ready to be published. All right, so this was about non-Gaussian cluster state. Now let's go towards scalability. Yeah, so this is the second aspect of making a fault-tolerant quantum computer. So you have to have many qubits. So like Google demonstrated a few years back in 2019, they demonstrated with, I think, 54 quantum bits. But you have to have like thousands or millions of qubits to do real quantum computing, something that a classical computer cannot do. You have to go with many, not really. I mean, you can do something that a classical computer cannot do even with small computers, but in order to do useful operations, you have to come up with very big quantum computers. So this was the first photonic quantum advantage demonstration from the group in China in 2020. So they used a lot of squeezed light, and they came up with a nice photonic quantum advantage experiment. The second one that recently came just a few days back was from the company Xanadu. It was published in Nature, and they did it more smartly. And I told you more smartly because of the following reason. So the first one is like spatial multiplexing. So you multiplex, so you enlarge your number of modes by using space, by using a lot of space. So you put a lot of squeezers, you take a lot of squeezers, and you take a lot of detectors and do it. So it basically takes a lot of space. That's why it's spatial multiplexing. But in this other architecture, they use time multiplexing. So what they did, they just took one single squeeze light, so just one single OPO, and then they played with fibers, rather, just like the one we have used in our cluster set setup. We use something called the delay line. So we keep the squeezed pulses rotating and rotating there. And using that, they made 3D cluster states up to like 216 modes of squeezed modes. You can compare not exactly to 216 qubits, but 216 Q modes, 216 continuous variable quantum bits are a big achievement actually. There are also other multiplexing schemes, like you can multiplex using frequency. It's the frequency multiplexing, or you can multiplex using the broadband resource as well. You can check this out. I do not have the scope here to go detail into it. The third element of making a useful quantum computer, making it full-fledged, is the fault tolerance, and maybe the most important of it. So let's dive deeper into what is fault tolerance. So fault tolerance means when you are able to do some quantum computation even with errors. So you are able to basically tolerate the errors that you make by using some error correction schemes. Just after making the measurement-based quantum computing paper, Robert Russendorf also came up with this idea of making it fault tolerant, how you can do error correction in a quantum computer, measurement-based quantum computer. And the idea was that you have to come up with a 3D cluster state. So you have to make a 3D cluster state to be able to error correct it. But in continuous variable regime, it's not sufficient to have a 3D cluster state because you always have errors, a lot of errors, and that comes basically because of finite squeezing. Practically, you should be, if you want to have a very good cluster state, then an ideal cluster state, then you have to have infinite squeezing, but we are limited. And because of finite squeezing, there's a lot of errors. But the good news is we can still have CV cluster states, 3D ones, and correct for the errors. And yeah, provide there is one catch, we can correct for the errors in 3D cluster states if we do not cross certain threshold. And this threshold is defined by the squeezing amount. So the state of the art, the best in the business, came from this paper, again from the group in Technical University of Denmark, is 13 dB. So if you make a cluster state out of squeezing sources, which is like 13 dB or more, then you can tolerate for the errors. But if you make a cluster state with like 11 dB or 10 dB, then you have a lot of noise and you cannot correct for those. The cluster states that I showed you are with like 5 to 6 dB, and that's pretty much like the state of the art. So we need a lot of squeezing.
Subhashish, you have 2 more minutes.
Yeah, sure. Thank you. So yeah, I'm pretty much done. So the idea is, yeah. So we already have a 3D cluster state, but we still need a GKP state because this is the ingredient that would give us a error correction formula for making a full-fledged CV quantum computer. And yeah, squeezing. So these things in the red is something that is yet to be demonstrated. So that's pretty much about fault-tolerant quantum computing. But I would like to, before ending up, I'd like to just quickly wrap up using a few more things here. Firstly, I would like to just summarize some important results that I gave you. So CV cluster state can be deterministically generated, and they are already generated in 2D and 3D. Non-Gaussian cluster state can be generated through photon subtraction. Thirdly, non-Gaussian quantum advantage is yet to be demonstrated. So we have non-Gaussian cluster states in principle, but then what we can do using those that a classical computer cannot do, that is something yet to be explored. Fourth, we need higher squeezing and GKP state. And yes, in the outlook, I would like to mention that an interesting platform is to go to continuous variable in microwave regime, because in microwave regime, we have a lot of squeezing that is recently demonstrated by the group, which I'm joining next for my further research. It's the group by Andrea Morello and Jared Pla. And they have demonstrated that they can produce squeezing up to 26 dB, which is like incredible. The world record that we have today is like 15 decibel of squeezing from the group of Roman Sanchpal in Germany. But in optics, that is not shown. So if we can take CV quantum optics to microwave regime, then we can do amazing things. It is believed, but yet to be demonstrated. Yeah. Also, we have higher nonlinearity, which would help us to generate GKP cluster states, GKP states to do error correction, and also there is more engineering freedom in microwaves because there's a lot of RF and microwave components out there. A lot of engineers working, so you can play around with the circuits. Yeah, of course, in terms of phase noise, they are more stable. So in optics experiments, phase noise is very annoying and you will always have them and you have to compensate for them. But in the microwave electronics domain, it's a bit easier to control. And most importantly, they can be integrated into chips. All right, finally, I'll just like to extend my heartfelt thanks to my previous group members. So this is Ulrich and Jonas, and then the leader behind the experiment, Mikkel. Mikkel was the hero behind all these experiments.